Hello, welcome to my talk on detailed derivation of Navier-Stokes equation. In this talk, I will give a brief history of Navier-Stokes equation, and then I will move to the general fluid dynamic equation and Euler equation. Then we will see the fluid viscosity and the total strength tensor. And then I will make detailed explanation on the viscous stress tensor. And last, the derivation of the complete moment equation for fluid dynamics, the Navier-Stokes equation. In the first two slides, a brief history of Navier-Stokes equation will be introduced. Euler in 1757 derived the Euler equation, the differential equation for the inviscid flows. And later on, the complete fluid dynamic equation would be considered as an extension of Euler equation by including the fluid viscous force. More than 60 years later, after Euler derived the Euler equation, Navier started the work using the pure molecular force as the fluid viscous force, and he derived the complete fluid dynamic equation. In 1827, Cauchy takes the fluid as a perfectly inelastic body, and introducing the symmetric stress tensor first time, which was based on his laws of motion for elastic bodies, the solid. Then in 1829, Poisson used the concept of fluids as temporary solids, and he also introduced the pressure into the Cauchy's symmetric stress tensor. Saint-Vallant in 1834 used the concept of molecules, slides, and approximations, which actually was very close to the derivation Stokes made. In 1845, Stokes studied the fluid friction on a pendulum, and he employed the Cauchy symmetric stress tensor to derive the fluid dynamic equation. His derivation is very similar to what we are seeing today in many textbooks. In 1934, Navier-Stokes equation was first named by Prandtl when he gave the lectures on fundamentals of hydro and aero mechanics based on the reference. As I have introduced, in Eulerian representation, the fluid domain would be discretized as many small regions, see here. In the Eulerian representation, the fluid states, including the density, pressure, and velocity vector. So the general moment equation for fluid motion would be given as this in the Eulerian representation for three moment equations on x-axis, y-axis, and z-axis, and also according to Euler's concept for the force acting on the fluid element. The force would be separated as the body force, the vector Fb, and the surface force, the vector Fs, and the corresponding component of the body force on x-axis and the surface force on axis are given all this. In this moment equation, we can see the first term on the left-hand side is the local acceleration, and the following three terms would be the convective acceleration. The force on the right-hand side, the body force per unit mass of fluid, the component Fbx, Fby, and Fbz. And the components of the surface force Fsx, Fsy, and Fsz per unit mass of fluid. In this slide, we will see the moment equations for Euler equation for inviscid flows. As I have shown in my talk, Euler equation and derivation with the detailed explanations. The moment equation for inviscid flows would be given as this. And this differential equation for inviscid flow is derived on a small fluid element. See this one. But here the element is enlarged for good illustration. Here we can see the body force is only from the fluid gravitational force. Thus, minus g here for the fluid body force per unit mass. And minus sign here means the gravitational force is in the opposite direction with z-axis. And the surface force due to the pressure is calculated as this, because the pressure would normally acting on the surface in the fluid. For a complete fluid dynamic equation, the missing part in the Euler equation is the fluid viscous force. As we know, all fluids are viscous. Thus, Navier-Stokes equation, the full fluid dynamic equation, would be an extension of the Euler equation by including the viscous force. But how? This is the topic in this talk, and in the following slides, the understandings would be made how we can add the viscous force into the equation. Firstly, we will have a look how the fluid viscous force is expressed. Newton, in his book Principia, defined the viscous stress. Now it is named as Newton's law of viscosity. So the viscous stress tau xy is given as the limit of this expression. Theta u is the velocity increment along the x-axis, and theta y is the spatial increment in y direction. Generally, we will express the viscous stress as the partial differentiation like this. That's because u could be also the functions of x and z. Here, the partial differentiation u with regard to y means the calculation is supposed when x and z are kept unchanging. And we can see here the unit of the viscous stress would be Newton per meter squared. If we somehow measure the viscous stress and we also have the gradient of the velocity, then we can obtain the fluid viscosity coefficient mu given as this. So this is the principle for getting the fluid viscosity mu. This fluid viscosity is also called the dynamic viscosity, with the unit as Pascal second. In fluid dynamics, another important viscosity is the kinematic viscosity. Mu is defined as mu divided by rho, with a unit of meter squared per second. In fluid dynamics, the kinematic viscosity might be more important than the dynamic viscosity, since for the kinematic viscosity we can compare the viscosity, for instance, air and water, since the kinematic viscosity is normalized by the fluid density. For fluid, the total stress tensor would be based on Stokes' assumption in 1845. The total stress tensor would be given as capital T double arrow equaling to 3 matrix. And the first matrix is the tensor for the pressure, and the second is the tensor for the viscous stresses, and the last term is the tensor for fluid compressibility effect. That means if the fluid is incompressible, the last term would vanish. So if we look at the fluid element in the region, so the pressure is made from the fluid outside the element. The direction here we see. This is why the tensor due to the pressure here minus P, because when we look at the normal vector for the surface, N would be opposite with P. That's why we got the minus sign here. And this is similar to the tensor for fluid compressibility. So this component would pointing normally to the surface, and the direction would be opposite with the normal vector. So we have minus sign here. And in this talk, the viscous stress tensor is the focus. So following slides would be made for the understanding of the viscous stress tensor. The fluid viscous stress tensor can be expressed as tau double arrow as matrix as this. So we can see here we have 9 expressions. And in some textbook, this matrix or tensor can be written as this. Here, the subscript 1 is equivalent to x, and the subscript 2 is equivalent to y, and 3 to z. But in my talk, I will use the first expression for the viscous stress tensor. So to understand this component for the viscous stress tensor, we need to consider a special cube, see here, which has 3 special surfaces: S1, the front surface; S2, the side surface; and S3, the top surface of the fluid element. All these surfaces are aligned with the Cartesian coordinates, see here. And we can see on the surface S1, x would be a constant, the front surface. And on S2, y would be constant, the side surface. And on S3, z would be constant, the top surface. Now on the cubic surfaces S1, S2, and S3, we can draw the component as this. On S1, we have the component tau xx, tau yx, and tau zx. So 3 components in 3 directions along x-axis, y-axis, and z-axis respectively. And similarly, on S2, we have 3 components, tau xy, tau yy, tau zy, along 3 axes. And on S3, 3 components, tau xz, tau yz, and tau zz. This type of drawing we can see in most of the textbooks. Following the book Marine Hydrodynamics, tau yx is defined as acting in the y direction. See here the first subscript. Upon a surface of constant x, the second subscript. So that means on the surface S1. While the stress component tau xy is acting in x direction, See here the first subscript. Upon a surface of constant y, see the second subscript here, y. So this is on the surface S2. So one question here, why do the stress tensor component have such directions? In this slide, the viscous force is calculated on a unit surface S equaling to 1, and the viscous stress force is calculated at the vector F stress equaling to the viscous stress tensor dot times the vector n. So if we write the tensor and the vector in detail, we have the expression as this, the tensor and the vector. So we can see the tensor, we have the dimension 3 times 3, 3 rows, 3 columns. And for the normal vector, we have 3 rows, 1 column. So times this together, we have a new vector. See, the dimension would be 3 times 1. So we have the expression in the first row is obtained by the first row of the tensor times the vector component and added them together. The second row of the fourth vector is the second row of the tensor times the vector and added them together. Similarly for the third component of the stress force. So we can see the dimension of the result would come from the row of the tensor and the column from the column of the vector. And here we can use 3 components of the force, Fx, Fy, and Fz, to represent all this expression. So we have the expression as this. But we can see here the stress on an arbitrary surface is quite complicated, and it is also difficult to understand. To simplify the understanding of the fluid viscous tensor, we look at the special cube, and on the 3 special surfaces S1, S2, and S3, we have very simple normal vector. For instance, on S1, M1 would be given as this. Only in the x direction we have value 1, and y and z directions we have 0. So on S1, the stress force would be calculated as the vector F S1 as this. So here we can see only 3 values here. And similarly, on the surface S2, the vector has 1 value on y direction given as this. So the force acting on the S2 would be given as this. Again, 3 simple components in the expression. And same for the stress force on S3, we have the expression as this. So we can see here on the specific surfaces S1, S2, and S3, we have much simpler force expression. And all these forces have 3 components. Now, based on the calculation in the previous slide, on the surfaces S1, S2, and S3, we can see how the fluid viscous stress components are orientated. On S1, the stress force vector Fs1 has 3 components, tau xx, tau yx, and tau zx. And we can see tau xx actually is on x direction, and tau yx is on y direction, and tau zx is on z direction. So for the stress tensor component, the first subscript means the direction of the stress force. The second subscript, OX, that means on S1. So if we draw the first component on S1, we have this tau xx, tau yx, and tau zx. Similarly, we can draw the stress force on S2. So we will have tau xy, tau yy, and tau zy. Again, we can see the first subscript x, y, z indicating the direction of the stress tensor. And the second subscripts are all y, that means on S2, for which y is a constant. And similarly, on S3, we have tau xz, tau yz, and tau zz. So these are exactly same as the one we showed before, and the one we can see in many textbooks. Now we are going to calculate the surface force due to the viscous stresses. In here, we look at the surface forces on y direction. Due to tau yy, the direction would be pointing y direction, and the force due to tau yy would be calculated as this. So here, this term is the stress tensor component on this surface given as this, since the distance between the surface and the center of the element is half delta y. And this term in the opposite direction, and the distance to the center of the element is minus half delta y. So the stress tensor component would be given as this. And these are the surface area S2 calculated as delta x times delta z. So we can see these are indicated by the black arrows. So if we calculate this expression, we have the simple expression as this. Since here tau yy and tau yy would cancel each other, and this term and this term make this. So we have the expression as this. Here delta V is the volume of the fluid element. And similarly, on the surfaces of the cube, now we calculate the surface force on y direction due to yz, which is calculated as delta Fy2 given as this. So this is the stress tensor component on the top surface, and this would be the stress tensor component on the bottom surface. And these two are the surface S3 calculated as delta x times delta y. So we can see the direction of the tensor component would be in different directions. And we can calculate this into the expression as this. And this is very similar to the previous expression. And also we can calculate the surface force on y direction. Delta Fy3 calculated as this. And this time is the stress tensor component on the front surface here. And this is the stress tensor component on the back surface here. So these are the surface S1 calculated as delta y times delta z. And we can calculate this into the expression as this and this. Now we can put all these surface forces on y direction due to the different tensor component. So the total surface force due to the viscous stress tensor component would be given as delta Fy1 plus delta Fy2 plus delta Fy3 given as this. So we look at the terms here. The partial differentiation would be the tensor component tau yx with regard to x, tau yy with regard to y, and tau yz with regard to z. And the corresponding surface force on y direction per unit mass would be given as delta Fy divided by rho delta V. So we have the surface force per unit mass on y direction given as this. So here you can see the first subscripts are all y, so that means the force would be in y direction. And the second subscript would be corresponding to the partial differentiation with regard to. So partial differentiation tau yx with regard to x, and tau yy with regard to y, and tau yz with z. Similarly, we can obtain the total force per unit mass on x and z directions due to the fluid viscous stresses given as fx with as this. So here we can see the first subscript for the stress tensor component would be x, and the force on z direction would be given as this, and the first subscript for the stress tensor component would be z. Now we come back to the total stress tensor, which now is written as this. Here we see the pressure and the effect of the fluid compressibility would have same feature. So in the derivation of the Navier-Stokes equation, the pressure and the fluid compressibility would be treated in same way. If we look at the Euler equation, we see the surface force is from the pressure only. We can, based on this, and take the pressure and the fluid compressibility together for the simple surface force. So we can have the equation with the fluid compressibility here, as well as the viscous force due to the viscous stress tensor. And in the previous slides, we already shown the fluid viscous force can be calculated from the viscous stress tensor component. See the viscous force on x direction, on y direction, and on z direction. And next, we will see how we can build the viscous force and the fluid velocity component. Since Stokes, the fluid viscous stress tensor is generally accepted as a symmetric tensor, and the components of the viscous stress tensor are defined as tau xx given as this, and tau yy as this, and tau zz given as this, and tau xy equaling tau yx would be given as this expression. Tau yz is the same as tau zy given as this, and tau xz equaling to tau zx given as this. Here, mu is the fluid viscosity coefficient, and for Newtonian fluids such as air, water, the most common fluids, under the normal condition, their viscosity coefficient would be constant, meaning they are Newtonian fluids. Now we look at the viscous force, the component on x-axis. From the expression, the first term would be given as this, and we can use the definition of the stress tensor. So we have the expression as this. Consider the Newtonian fluid, mu is a constant, so we can have this. Here, nu is the kinematic viscosity, defined as this. We have seen this before. And the second term in the expression would be calculated as this. So we use tau xy here into the expression, so we can obtain the expression for the second term of the stress force on x direction. And the third term of the stress force on x direction would be given as this. Here, tau xz are substituted. So we have the expression as this. And if we put all this together, the viscous force on x direction would be calculated as this. This is from the first term, second term, and the third term. So we can write this in a different way, put this together, and the rest term would be like this. Here we use the Laplace operator, this. Therefore, we can have the expression as this. Here, in this expression, we can take the partial differentiation with x out of the bracket. So we have the expression as this. And we see in the brackets, this is the expression as the divergence of the velocity vector. Therefore, we can express the viscous force in x direction given as this. The corresponding moment equation on y direction would be given as this. So if we compare this momentum equation with the momentum equation on x direction, we can see the velocity component on y direction, v, here, and here. And the gradient would be with regard to y, here and here. And all other terms would be same as the one in x direction. Similarly, on z direction, the momentum equation is given as this. It is very similar as that direction. Here we use w, the velocity component on z direction, to replace the velocity component u here, and the gradient with regard to z instead of the gradient with regard to x. The only difference on z direction is the fluid body force, the fluid gravitational force minus g here. Now in this slide, we put these momentum equations together. So on x direction, the momentum equation is given as this, and this is the momentum equation on y direction, and this is the momentum equation on z direction. So all these three momentum equations are the momentum equations for Navier-Stokes equation. So here we can see we have three momentum equations, but we have four unknowns, the pressure P, and the three velocity components u, v, and w. So this is even for the incompressible flow. Thus, for incompressible flows, for a complete fluid dynamics, we need one more equation, and the equation would be the continuity equation. For compressible flows, more equations would be needed, such as Gauss equation for the compressible air. And if energy transfer is involved in the fluid dynamics, we need energy equations.